Look at a nuclear power plant, and it is natural to wonder how engineers manage to build something of this magnitude. Millions of tons of steel and concrete are assembled into fortresses that dominate the landscape. Reactor construction creates a custom-built housing designed specifically to contain and sustain a continuous neutron chain reaction. To see how these structures come together, we will deconstruct the global standard, the baseline light water reactor, or LWR. Every design choice in an LWR is governed by the neutron economy. From the outer walls to the innermost pipes, every building material is selected based on exactly how it interacts with free-flying neutrons. Understanding the gargantuan concrete structures on the outside requires us to first reverse engineer the physics happening at the microscopic center of the reactor core. This is the absolute center of the reactor construct, the nuclear fuel pellet. These are made of uranium dioxide. Engineers select a ceramic matrix of uranium dioxide over pure metallic uranium. While metallic uranium melts at a relatively low threshold, the ceramic structure withstands the extreme internal temperatures of fission without liquefying. Ceramic pellets release radioactive gases during fission that require physical containment while allowing the chain reaction to continue uninterrupted. The pellets are stacked and sealed inside the first engineered structure of the core, the cladding tube, forged from a specialized alloy called zircaloy. This chart shows why zircaloy is used. While zirconium possesses the physical strength to hold back pressurized fission gases, its extremely low neutron absorption cross-section makes it transparent to thermal neutrons. The fundamental building block of the entire facility balances these two needs, holding back extreme physical heat while allowing subatomic physics to pass through. Individual clad rods are bundled into precision-engineered fuel assemblies. They are arranged in a strict geometric lattice that ensures neutrons have the correct spacing to sustain criticality. An unthrottled lattice is dangerous. The neutron population will grow exponentially and generate enough heat to melt the assembly. Control rods, manufactured from silver, indium cadmium, or boron carbide, provide the necessary braking mechanism. These rods act as parasitic neutron absorbers. Sliding downward into the fuel channels, they capture free-flying neutrons, killing the chain reaction and dropping localized heat. Operators manipulate their vertical depth millimeter by millimeter to actively steer the core's thermal output. Moving these rods with absolute fail-safe precision requires the massive mechanical infrastructure seen here in this dense array of drive mechanisms. The reactor core functions as a volatile, living geometry that must be continuously and mechanically throttled to prevent self-destruction. The first major macrostructure is the housing built around the core to capture its heat, the reactor pressure vessel, or RPV. The immense forging process uses low-alloy carbon steel, which is then internally clad with stainless steel to prevent corrosion. The RPV meets a strict thermodynamic requirement, holding the primary coolant water at over 15 megapascals. This high pressure keeps the water from flashing into steam, even though it far exceeds its normal boiling point. Beyond pressure, the RPV faces constant, decades-long bombardment by fast neutrons escaping the core. This exposure leads to neutron embrittlement. At the molecular level, fast neutrons strike the crystalline steel lattice, causing microfractures that gradually degrade the structural integrity and malleability of the steel.
The RPV faces a specific combination of engineering challenges. It must endure thermodynamic pressure alongside radiation-induced degradation. The primary coolant loop connects the RPV directly to the plant's steam generators. This primary water serves two roles. It is the hydraulic medium that transfers heat, and the critical neutron moderator that slows down fast neutrons so fission can continue. Engineers must account for a total rupture of this high-pressure loop. This worst-case scenario dictates the construction of the containment building, the final layer in the plant's defense in depth. The dome consists of a leak-tight steel liner surrounded by meters of heavily reinforced post-tensioned concrete. The dome's massive volume is mathematically calculated to provide enough empty physical space to capture and depressurize the flashing steam from a pipe rupture. The towering concrete skyline is a gigantic safety net, scaled specifically to the explosive potential of pressurized water.
A fully operational plant functions as a single unified machine, where every macro-scale structure is a direct result of microscopic physics. The nuclear physics of the uranium dioxide pellet dictates the specific metallurgy of the zircaloy cladding. The heat output of that cladding dictates the thermodynamic requirements of the forged steel pressure vessel, and the explosive pressure inside that vessel dictates the civil engineering of the post-tensioned concrete dome. This entire fortress exists solely to foster and control the active glowing reaction at its center. Reactor construction is an exercise in architectural equilibrium, forcing extreme forces into a state of perfect sustained